Imagine a world where you can treat or even reverse excessive scar formation, also known as tissue fibrosis. Up to 45% of deaths worldwide are caused by fibrotic disease, for example in the heart, in the lungs, or in the liver. Imagine your body is like a bustling construction site, always fixing and repairing. When you get a scrape or a cut, your body jumps into action, just like builders repairing a broken road. When your body fixes itself, it's like a big team effort. Lots of cells, including special cells called pericytes, transform into these builder cells called myofibroblasts, which rush in to make a tough material called collagen. Collagen acts like a cement that holds everything together, acting as a quick fix to keep you from bleeding and developing infections. But sometimes these myofibroblasts work too hard, piling up too much collagen, like builders who break up an organized mosaic of tiles with too much cement, a bit like this road in Birmingham, making the repaired area stiff and hard. This is called fibrosis, which can lead to organ failure and death. Usually, scientists use animal models and basic two-dimensional cell culture models to help them better understand the disease and to test drugs before they go to clinical trials. However, these basic cell culture experiments involve growing cells on flat plastic surfaces, which is inaccurate, and animal models are technically and ethically challenging. This is where my research comes in. I combat this problem with more complex three-dimensional cell culture models that are more efficient and are more similar to the human disease state. This is important to reduce animal testing, which is expensive and takes a long time, and to help get drugs on the market quicker. Therefore, I'm developing complex cell culture models, which is a bit like building a road. I use human cells called pericytes and endothelial cells, which are the cells that line your blood vessels as building blocks, in a tunable cement called a hydrogel that we tune to have the consistency of the specific human tissue of interest so that the road mimics what's happening inside of the body. Consistency is key. Hydrogels, or the cement, which is too stiff, will be impossible to work with, but if it's too liquid, it won't repair the road. Then I add drugs to the model to see how this changes the cell's behavior and the hydrogel structure to understand cells' transformations and to mimic fibrosis. So far, I have established that certain drugs cause cells to transform into these builder cells quicker, which makes the cement thicker and more problematic. My research will make it possible to understand this process better, finding ways to stop fibrosis from happening or even to reverse it. 45% of deaths worldwide are caused by fibrosis. Achieving scar-free healing within a generation will improve patients' lives.